Hi all, welcome to part 8 of the video lecture on counters. So from part 1 to part 7 we discussed something called asynchronous counter mainly. So started with what is a counter and difference between synchronous and asynchronous counter. Those things we discussed. Then we move on to asynchronous counter in detail and we saw many variations of it. So how we can asynchronous counter basically means the output of we will apply the clock directly only to the first flip flop and its output will act as a clock to the second one, like that. So it's basically a frequency divider and that further leads to that counting. So that concept we clearly understand in the previous video. Now from here onwards we will discuss something called a synchronous counter. So we already seen many problems with asynchronous counter in the last video. So it's like it's basically called as a ripple counter, right? I'm talking about asynchronous counter. Ripple counter means what? So there is delay, right? So every flip flop can work only after getting the clock signal from the previous one, because the output of the previous flip flop is being given as the clock's pulse for the other one, right? The one which is following it, and that time it has to wait till the output is being generated. So accordingly there will be some small delay and that will lead to something called transient states. So those things we saw already, right? So like that many minute problems are there with asynchronous counter. So it's always better if we can come up with the synchronous counter. So synchronous counter, the speciality is all the flip flops are triggered by a common clock. So that is the first thing you have to note down. So asynchronous counters are different from ripple counter or the asynchronous counter in that the clock pulses are applied to the inputs of all flip flops simultaneously. A common clock triggers all flip flops simultaneously rather than one at a time in succession, as that in the ripple counter, right? And the decision whether a flip flop is to be complemented or not, whether it should do that toggling. So the counting is basically each bit you are toggling in some fixed way, right? So that is what is happening. So sometimes you want to toggle if you are looking at least significant bit in any up counter or down counter, so that will continuously toggle. But the other bits are like they are sometimes they will toggle, sometimes they will not toggle, right? So that is being determined by the from the values of the data input such as t or and also the clock, right? So anyway we will see the design. That time this concept will be clear to you. So sometimes we want to toggle or sometimes we don't want to toggle, so that we have to clearly identify, and that we will implement using the normal combination circuit gates. Okay, so this is the basic. So before moving on to synchronous counter, I just want to refresh some of the concepts that we already studied, particularly for any synchronous sequential circuit. And these things actually we discussed in our offline classes, and I'm refreshing it again. So if some of you missed the classes and also you can follow from this. Okay, so that about it. So synchronous clocked sequential circuit. So basically, sequential circuit, any sequential circuit, if you are looking at it, is a combination circuit only, but there will be something called a feedback path, right? So the output of the combination circuit we will be giving back to the input through some feedback path, and that feedback path will typically contain the memory element or the storage element. So latches and flip flops are main storage element. So in all the subsequent design we will see only flip flops because they are clocked latches, right? So it will work in synchronization with the system clock. So that is what makes flip flops better than the latches. Anyway, storage element by default you can assume flip flops, and all those flip flops are being triggered by a common clock. So that is the meaning of something like this. Every flip flop, how many you are using, all are commonly triggered by this clock, and input will be there, output. In this output, the output is actually depending on the present input as well as the previous output, like this, right? This is a block diagram of any sequential circuit, actually, particularly synchronous sequential circuit. So what makes it synchronous? By this something like this, because the clock, addition of the clock that trigger all the flip flops simultaneously, that is the meaning of this kind of a notation. So that makes it synchronous. And there will be a timing diagram for the clock like this, and during every rising edge or something, whether you are having positive edge triggered or negative edge triggered, the flip flops will be triggered. And now another thing we already saw is the characteristic table. Hope you remember. So this is what we discussed throughout the discussion of the flip flops. Suppose so mainly SR, JK, D and T flip flop is studied, but in most of the cases we will focus on this JK, D and T. So they find applications mainly because SR there is a problem like a particular input to combination when both s is equal to 1 and r is equal to 1, that is not used, right? So that will lead to something called directly if you are applying s is equal to 1, r is equal to 1, there is no issue actually. It will lead to some stable output only, but the problem is immediately after that, if you apply the no change, it will reach some undetermined state. So we don't want it, right? So we are not allowing that particular input to combination. That is the case. So a more generalization of this same SR, it is JK. So it works like SR only. In addition to that, this S is equal to 1, R is equal to 1, that is also having a meaningful definition here. For J equal to 1, K equal to 1, here it means toggle, right? So that is why mainly we will focus on JK, and advanced version of it's not advanced and something like both J and K we are combining and giving a common input like a T, so we call it as a T flip flop. So that's particularly for toggling. If you want to toggle the circuit, make T is equal to 1. Otherwise, if you want to return the previous information, give T is equal to 0. So that is the way it is working. It finds many application for this counter and register design. We already seen it, right? And D flip flop also another one where whatever you are applying to that D, that will come as the output. Yeah. That about it. Anyway, you know this table, right? So J S is equal to just like that, J equal to K equal to 0. 0 0 means no change. 0 1, I mean whenever this S equivalently we have J, right, is equal to 0 and K is equal to 1. I mean K is equal to 1 or R is equal to 1, making the circuit reset. Okay. Similarly here this 1 0 corresponds to setting the circuit, and 1 1 corresponds to toggle. Whatever be the last Q of T, its complement you will get, that is toggling, right? Similarly, D flip flop, on this having only reset and set mode. So if input is 0, it will reset. That is output is also 0. If input is D input is 1, it will set. That's all. T flip flop is again only two input like 0 or 1. 0 for no change and 1 for complement. And these things you know clearly, right? And accordingly, there is something called as characteristic equation. I just added this also. This also I discussed in the class. Like sometimes they at this point I thought of telling you about this, because sometimes they may ask you what is a characteristic equation. So that is that kind of a question I saw in previous university exam question paper. So derive an expression for the characteristic equation of JK flip flop like that. So it's a very simple concept. This characteristic equation is simply another way of representing the characteristic table. So from this characteristic table only we are deriving this characteristic equation. Let me just tell you how to come up with the characteristic equation of this JK, so that you can find out others also. Okay, so D is something straightforward, right? At any point, what is the Q output at a T plus 1 the clock cycle? It is nothing but the current value of the D input. That's all. So the Q output is nothing but D. So this is straightforward, right? So for this one. But what about this Q output of the JK flip flop? That is actually J Q bar plus K bar Q. So like that we are having, it is actually the table we are representing in this way only. But I will quickly tell you how to come up with this. See. So we already know the characteristic table of JK, right? So we have a number of ways to derive that characteristic equation. I will discuss on straightforward way. Okay. So our outputs are like J, K, and sorry, our inputs are like a Q. As a function of J, K and Q, you are getting the next value of Q. So it is typically denoted by Q of T plus 1. So this Q means, this Q here means Q of T. Q of T is simply denoted as Q, because in the equation they used that Q. That is why I also taken like a Q, right? If you want, you can take it as Q of T, fine. So that about it. Now tell me different combinations of the input. So at any time, so you know that, so this output Q at the clock cycle, some T plus 1 the clock cycle, is a function of the current input JK and the past output Q or simply Q of T. So Q of T you can denote as Q. Okay. So both the same. Now the different combinations are, you can fill the table, right? 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 1 0 1 1 1. I hope I mentioned all the 8 combination. Fine. Now tell me, in each of these combination, what is your Q? I mean, so J, J equal to 0, K is equal to 0 corresponds to what? No change, right? No change. So this corresponds to no change. So no change means what? So these two corresponds to no change. I mean whatever be your this Q and in the previous clock cycle, that will just retain in the output. Okay, similarly this 0 1 means what? 0 1 means what? J equal to 0 and K is equal to 1. This corresponds to resetting the circuit. Hope you remember, because K equal to 1 for resetting, right? So resetting the circuit. So whether you are having, okay, let me use a different color. I just want you to understand this clearly. So J equal to 1, 0 and K is equal to 1 corresponds to resetting the circuit. So whatever be the last output, it will reset irrespective of this. Here it is not changed. That is why the 0 1 retained as 0 1. But here it is resetting, right? Now similarly, this one. 1 0 corresponds to setting the circuit. So from where I am getting this, that is from the characteristic table only, because I know it. This is how it is working. So irrespective of this last value of Q, it will set the circuit. And finally, this 1 1 corresponds to toggle, because it is JK. So how it will toggle? 0 will toggle to 1 and 1 will toggle to 0. So this is the idea. So this is how you are getting the truth table. Now you know how to simplify it using K-map, right? Now I want you to simplify using K-map. So K-map, one second. So I want, I will draw it just. As I drawn that template of K-map, now you can fill the value. These are all corresponds to. So here 1 is 1, then other cases are 0, then this is 0, 1, 2, 3, 4, 5, 6, 4, 5, 6, they are 1, others are 0. So now how can you simplify this? So you can make this as a group, and this you can make as another group, right? And from that, so this is a table for, so this is the table for Q of t plus 1. So from that you can write Q of t plus 1 as a function of J, K and Q. So just look at that K-map and just try. So if you are looking at this corner grouping, you will get 0 to 1, J, K is getting cancelled, and Q bar, J is 1, so J Q bar, right? Similarly, this corresponds to J Q bar. Similarly, this grouping corresponds to, here J cancelled and K bar Q. Okay, so it's something like a K bar Q. So this is the characteristic equation of this JK flip-flop. So J Q bar and K bar Q, right? Similarly, you try for that TK, you will get that, T flip-flop, you will get it like the XOR of T. J, the same thing only, because in JK, how can you convert this JK to Q? It's very straightforward, because from here, or the same procedure that I discussed, you can try here also. Okay. So from here, when it comes to T flip-flop, this J equal to K equal to simply T. So that Q of T plus 1, you can write like J, you replace with the T, Q bar, plus K also you replace with the T, so you will get this. So this is nothing but T XOR Q. Okay, so you can write that way also, and or in the way I discussed here. SR flip-flop, I request all of you to try like this. You will see what is the characteristic equation. Okay, so there are different ways also. This is one way of doing it. So characteristic equation is nothing but the same characteristic table I represented in using a single equation. That's all. Now there is something called direct input. This also we discussed. Like sometimes we want to set all the flip-flops irrespective of the current value. So that is what is our preset input, or we call it as direct set also. And clear input is something where we want to clear all the flip-flops or reset all the flip-flops. So now I just want you to think yourself or try read from the textbook, like how this preset and clear are being incorporated into the flip-flop, because for the flip-flops we have that different input to combination, but whenever this preset is equal to 1 or by default they are active below, so whenever this we are giving a 0, it will be activated. So whenever this preset is equal to 0 or clear is equal to 0, accordingly the flip-flop should be set or reset. That should happen. So that implementation you try to see yourself. Okay, anyway, now you know that at any time in any design, if you saw this particular pin, by default they are active below. So whenever I am giving a 0, that it will reset or clear, and whenever I'm giving 1 it will set, or it's something called a preset. Okay, so that concept you know. Now there is another important concept called excitation table. You know what happened in the characteristic table? What is this characteristic table? The output you express as a function of the input, right? So characteristic equation also. So what is your q of t plus 1 as a function of the input, that is j, k and q. I mean the last output is also an input to the circuit, right? So what is your output as a function of the input is what we call as a characteristic equation, or it's something like the truth table. But there is another table that which is of interest, because in counter design everywhere we will see this way, an equally important concept called excitation table. Excitation table give you the reverse thing, like for a given output transition, so I want the output to be changed like this, what should be the possible input, right? So to have this kind of an output transition, what is the input? So you know, so this also I discussed in the offline class. Anyways, revising it again. So this is something like a so this is a current value. So it's like a q of t, and after on clock cycle what is the output? Okay, so either you represent like this, a more better way is like a q of t plus 1. 1 second. Yes, so these are all notation, right? In different textbook they are having different notation. So here they mean like this is a past output and this is a output after on clock cycle. So maybe like a q of t and q of t plus 1 like that. So this is something I am comfortable with. Anyway, both you can use fine. So and this also you know, right? So it's like currently I am having 0. After on clock cycle also I want to retain this 0, right? So I can achieve this 0 by either retaining the last information, right? Either retaining the last information. So this particular combination I can I will get. I mean already it is 0 now. After on clock cycle also I just want 0. So one thing is you just apply j equal to 0 and k is equal to 0, that will retain the information. Another thing that you can try is you give j is equal to 0 and k is equal to 1, so that the circuit will be resetting, so that you will get this 0. So both are fine. So together you can write it as j equal to 0 and k can be 0 or 1. So that is why this don't care is coming. Okay, clear. Now similarly, what about this? So this is like I am having this 0 currently, and after on clock cycle I want the output to be 1. So I can achieve this in two ways. So one way is like toggling, right? So the 0 is changed to 1 is actually toggling. So j is equal to 1 and k is equal to 1, so that will toggle the circuit, right? Another one is you can simply set it. I don't know whether it is so. Right now I am having 0. After on clock cycle I am getting the output as 1. It can be due to toggling, right? So what kind of input is needed? So that is a question, the reverse question, right? Or it can be due to setting the circuit. So how to set the circuit? It is like a 1 0. When you apply 1 0, circuit will be setting. And you know, this is fixed and this can be anything. So like that you are having this 1x here. Similarly, the other one 0 toggling, right? X1, this one, and you understood, right? Similarly for T flip flop, it's very easy. 0 I want to change it to 0, so this is retain. For retaining, T should be 0. Here toggle I want, so T is equal to 1. Here I want again toggle, so T is equal to 1. Here I want to retain, so T is equal to 0. So that is easy, but for JK you have to think like two ways you can achieve it. That is why we are writing using that don't care. Okay. Similarly, SR and D also, you try it out, you know it. So this is something very much essential. We will see where it finds application, because for the counter design everywhere we will see this. Okay, so that about it. So what I thought of giving. So before starting, that's the next video onwards, we will see the direct design of any synchronous counter. And the thing is like for these are all the basic understanding you are supposed to have before starting the counter design, synchronous counter design. So what is a synchronous sequential circuit in general, where we are applying the clock signal simultaneous to all the flip flops. Okay, so that is the main idea. I mean in register everywhere we saw this only. All the registers we saw are synchronous in nature, right? Counter only we saw that asynchronous counter something and differently we saw, and frequency division that in that part. But most of the by default some synchronous sequential circuits are of synchronous in nature, okay, and that you know, and also what is the characteristic equation and characteristic table and this excitation table. So you have to be very much clear about these terminology, because so that you can expect this question. So differentiate between, or what is excitation table of something, what is characteristic equation, like that they can ask you the question. Fine. Now thanks for watching. In the next video we will see design of a particular synchronous counter.